Metal organic frameworks have potential applications for a wide variety of separation applications. In publications on metal organic frameworks, it is common to fit unary isotherms to determine the separation selectivities using IAST, and the unary isotherms are also fitted to determine the isosteric heats of adsorption. I'm going to examine the methodologies for fitting unary isotherms and MOFs, and to start the discussions, I'm going to use an example from a recent publication that is listed here. The paper reports unary isotherms for carbon dioxide, ethene, and methane at two different temperatures, 273 Kelvin and 298 Kelvin. The unary isotherm data is fitted to determine the isosteric heat of adsorption, and the isosteric heats of adsorption are plotted here, and the IAST calculations for the adsorption selectivities at 273 Kelvin and 298 Kelvin are plotted here, and these graphs are all taken from this publication. It's quite interesting to see the curious nature of these QST versus the uptake plots, especially for methane. Carbon dioxide also appears to show a non-linear behavior. Let's examine the reasons behind this. For determining the isosteric heats of adsorption, it is commonplace to fit the unary isotherms using the Vidiel fits, and the Vidiel coefficients for ethene, CO2, and methane are shown here, where A0, A1, A2, A3, A4, B0, B1, B2 are the constants in the Vidiel equation. The isosteric heat of adsorption can be determined from the Vidiel fits, and this results in the QST versus uptake plots that are taken from this publication. For determining the selectivities using IAST calculations, a different fitting procedure is commonly employed in the published literature. Sticking to the example for cadmium MOF, the unary isotherms are fitted with the Langmuir model for each of the four components: ethene, CO2, and methane, and the Langmuir fits are determined for each temperature separately. For example, this table here taken from this publication shows the fitted parameters A and B. This is the saturation capacity A. This is the B coefficient for in the Langmuir model at 273 Kelvin. This is the same data at 298 Kelvin. It's interesting to note that for each of the guest molecules, the saturation capacity at 273 Kelvin is fitted with, in this case, 16.6, and at 298 Kelvin it is 24.21506. For each of the other guests, the saturation capacities are different at these two temperatures. I put it to you, there is no a priori reason to expect that the saturation capacities are temperature dependent. And also, I do not see the rationale for using two different types of isotherms fittings. The Virial fits for determining the isosteric heat subabsorption, and the in this case the Langmuir fits for determining the IEST values of the adsorption selectivity. I would propose a completely different procedure in which we use isotherm fits in a different manner, and the same isotherm fits are used for determining the isosteric heat subabsorption and the adsorption selectivities. My procedure for isotherm fitting is to use, say, the Langmuir model, in which the parameter B is temperature dependent and expressed in this form. For each guest molecule, the entire set of data at different temperatures can be fitted simultaneously to determine the saturation capacity Qsat, the B naught parameter, and the energy parameter E. This fitting can be done with the Excel solver. As an example, I show here the Unary isotherms at 273 Kelvin and 298 Kelvin, the experimental data being fitted with a T-dependent Langmuir model shown here, where the saturation capacity is 16.7 moles per kilogram. The B naught parameter is 1.479 10 minus 9 per Pascal, and the energy parameter is 20 kilojoules per mole. The same thing can be done for CO2 and the other gas molecules. For plotting purposes, I use not the pressure, but the surface potential, phi, which serves as a proxy for the spreading pressure. Phi equals the spreading pressure times the surface area per kilogram of adsorbent divided by the gas constant R divided by the temperature. And this is given by the integral Q, which is the Unary isotherm at divided by P times d of P of or F, where F is a dummy variable. So for the single site Langmuir model, phi is simply Qsat ln 1 plus B times P, and the dependence of the molar loading on the surface potential is a unique graph for each temperature. I refer you to my presentation on the spreading pressure concept on my YouTube channel for details on the concept of the spreading pressure. The important advantage of this method of fitting is that the isosteric heat subabsorption can be determined by analytic differentiation of the isotherm model. And for the single site Langmuir model fitting, the Values of the QST for C2H2 and CO2 are respectively 20 kilojoules per mole and 18.5 kilojoules per mole respectively. Compare that with the values obtained from the virial fits. I do not like the use of the virial fits to determine QST because you need to fit the isotherms in two different ways, and the virial fits leads to some odd behavior in the QST versus uptake plots. I often see in the literature that the experimental data in the unary isotherms at any temperature is fitted using the dual site Langmuir-Freundlich model, even though for that particular guest host system, this is an overkill. I gave an example here of the unary isotherms for ethane and ethylene in a MOF, and the experimental data are shown here and fitted with the DSLF model using commercial software. The commercial software, if asked to fit the unary experimental data, produces 6 parameter values as shown here for ethane, and the 6 parameter values for ethylene are shown in this column. We note that the saturation capacities are unrealistic. 14.002, 4.82, and we see that the experimental data only shows a saturation capacity which is perhaps 5.5 for ethane and 4.5 or thereabouts for ethylene. So asking a software to fit the parameters yields saturation capacities and Freundlich exponents that do not seem to have any physical significance. Indeed, I've taken this data and fitted it with a single site Langmuir model to an accuracy that is acceptable. So the use of a dual site Langmuir-Freundlich model in these two cases is definitely an overkill. But there are also serious consequences on using the dual site Langmuir-Freundlich model, because extrapolation to lower pressures or higher pressures than in the experiments is fraught with danger, because the extrapolated values are crucially dependent on these Freundlich exponents. So the conclusion I would like to draw is that only introduce the Freundlich exponents and the additional sites if it is strictly required. Use Ockham's razor and choose the simplest model and increase the degree of complexity of the model only if the data demands it. In the previous slide, I had mentioned Ockham's razor. This is a philosophy put forward by William of Ockam in the 13th century. William of Ockam was an English Franciscan friar who put forward the philosophy do not complicate things beyond necessity. And this is termed the Ockham's razor. I summarize in the slide the philosophy that I adopt in choosing the isotherm model for fitting experimental data on the unary isotherms. Applying Ockham's razor, I start with the simplest model, the single-site Langmuir model to start with, as shown in the foregoing two slides for barium RPZ. Only if the single-site Langmuir model is of inadequate accuracy do I proceed further to refine the model. And then I go one step up and choose the two-site Langmuir model with two different sites. And this is required if there are isotherm inflections. For example, if I have adsorption of say normal butane or isobutane in MFI zeolite, where the isoalkane locates preferentially at the intersections, the unary isotherms show strong inflections that can only be captured by a two-site Langmuir model. So the next choice would be this one, and only if this fails do I proceed further to invoke the two-site Langmuir-Freundlich model, where we have the Freundlich exponents nu A and nu B. In very special cases for isotherms of water and some alcohols in MOFs and zeolites, and for flexible MOFs, we may need to even go further and adopt the three-site Langmuir-Freundlich model. So the recommended procedure is to start with the simplest model and increase the level of complexity as demanded by the experimental data. Let's examine the experimental data for the unary isotherms for propine and propene in ZnU2. ZnU2 is TIF6 copper TPA, and the experimental data are taken from this publication. The data for both components show isotherm inflections, and certainly for propine, the isotherms are also rather steep, and the single-site Langmuir model fails to capture the isotherms for both guest species. The dual-site Langmuir model also fails, and we need to resort to the dual-site Langmuir-Freundlich model. Now, what I generally do is to fit the data at the three different temperatures simultaneously using the Excel solver. Let's see how we do that. Let's fit the experimental data at the three different temperatures using the dual-site Langmuir-Freundlich model. Now, the parameters BA and BB are taken to be temperature dependent, with the energy parameters EA and EB. So for each guest species, there are 8 parameters to be fitted. QA sat, BA naught, EA, nu A, QB sat, BB naught, EB, and nu B. I determine these 8 parameters simultaneously using the Excel solver. But I do not do this blindly because I want to ensure that the parameter values are realistic. And if I use the Excel solver, I have the freedom to choose the saturation capacities such that the values are realistic. For example, for propine, the fitted parameters are shown here. You note that the QA sat value is 6, then the QB sat value is 2.5. If you add them together, we have a saturation capacity of 8.5, which seems to be reasonable because that is what the experimental data shows. The graph here plots the molar loading as a function of the surface potential. The surface potential is the proxy for the spreading pressure, and for the dual site Langmuir model, the analytic expression for the surface potential is derivable and is shown here. The advantage of using the surface potential as x-axis instead of the pressure is that the entire data set at 3 different temperatures collapses to a single curve for both gas species. And this is a convenient way to see if the fits are of good accuracy and representative of the experimental data. Also look at propene. We see the saturation capacity fitted is 4.4 and 2.1. If you add them together, we have 6.5. That's about correct. So we get realistic values because we can, in using the Excel solver, we can ensure that the fitted parameter values are realistic. Note also that I have here chosen the second Freundlich exponent nu B to be unity in both cases, because perhaps only one of the Freundlich exponent needs to be different from unity. And we note also here that nu A value is 1.24 and nu A value for propene is 1.3, close together. So fitting the isotherm data with Excel ensures that we get physically realistic fit parameter values that allows safer extrapolation to lower pressures than measured experimentally in the isotherms. Such extrapolation is important for C3H4, C3H6 separations because the feed mixture may contain only 1000 ppm of propine, and we need to reduce the propine content to less than 40 ppm. And further advantage of fitting the DSLF model with temperature dependent parameters is that the isosteric heat of adsorption can be determined by analytic differentiation of the isotherm parameter fits with temperature dependent BA and BB parameters, as we shall see in the subsequent slide. From the dual site Langmuir-Freundlich fits with temperature dependent BA and BB parameters for propine and propene in ZnU2, we can determine the isosteric heat of absorption using this expression by analytic differentiation of the DSLF model. The analytic differentiation can be carried out using Mathematica or Maple and can be easily programmed in Excel. The calculated values of the isosteric heat of absorption for propine and propene are shown here using the fit parameters for ZnU2 as shown in the previous slide. This data has been published in this paper. For fitting unary isotherms, we need to adopt the Ockham's razor. Do not complicate things beyond necessity. We start with the simplest physical model, the single-site Langmuir model, and only resort to more complex models such as the dual-site Langmuir model or the dual-site Langmuir-Freundlich model if the unary isotherm data cannot be described adequately using simpler models. For example, isotherm inflections require the recognition that there may be two different sites for adsorption within the MOF framework. If the isotherms show steepness, such steep isotherm behavior requires the Freundlich exponent to properly capture them, such as the case with flexible MOFs or with guest molecules that undergo molecular clustering. The isotherm data at different temperatures can be fitted simultaneously using temperature dependent parameters, and the advantage of this approach is that the T dependent parameter model can be differentiated analytically to determine the isosteric heat of absorption. Once the isotherms are properly fitted with the appropriate physical model, then the adsorption selectivity calculations can be carried out. And for this purpose, you may watch my YouTube presentation on the IAST.